Hello everyone. Okay, we can proceed in our class. So in this class, what we will do, we will talk about the questions and answers totally dependent on quark model as well as the chromodynamics, like some part of the quantum chromodynamics will be there and some part of the quark model will be there in our today's lecture. So basically what I am going to say here, as I already told you that four interactions were there in our nature. So four interactions means like there are obviously all the things are known to all of you. That four interactions means the first one is gravity, which is very much small in like very less interactive, and the second one is EM, third one is weak, and the fourth one is strong. Okay, so these four types of interactions are present in nature, but right now we will not talk about gravity because it's a very small interactive nature, and obviously in our nuclear and particle physics reason that gravity will not work that much, so that's why we are not talking about gravity here. We will only talk about electromagnetic weak and strong interactions in our lecture. So basically, if we are talking about any nuclear reaction, this nuclear reaction can do something which obviously, like let's see one interaction, that x plus x. I already told you before that small y plus capital Y. This type of interaction, if it is there in any nuclear interaction, then what is the nature of that interaction we have to know. Like obviously, total nuclear and particle physics questions as well as quark model questions are based on that type of question. That let's say one nuclear interaction is given, you have to say that what type of interaction it is. Is it EM? Is it weak? Or is it strong? Right. So to do that, I have made a table here. Table means it's a very important table, I thought, so that's why I have put it here, this type of table. So here what is in the table, in the left hand side all the quantum charges are given, and then conjugate, may or may not conjugate, and not conjugate. So what does this means? Basically, S is the strangeness quantum number. As I already told you, like I think you all might know that S is the strangeness quantum number. So when the strangeness quantum number, hello, hello, can you hear me? Hello, Ravindra, can you hear me?
Yes, ma'am, yes.
Okay, I don't know why the people are not coming today. Maybe there is some holiday or something. I don't know. I was just waiting till 5 p.m. but still there is no one, and you are the first one here. So, is there
Yes,
any
ma'am.
holiday today?
Today, ma'am, actually it is Sunday, no, ma'am. Only.
Yeah, Sunday
No,
is obviously holiday, but I don't know why these people are not coming today. Okay, whatever. So, you were present in the last class, right?
last, ma'am.
Yes. Oh, okay. So in that last class, we were talking about some, like I was talking that in that today's class we will talk about some question about quark model and quantum chromodynamics, and obviously one of the student also said to me that please do some questions on that topic. So that's why I came here with some questions. So, but I don't know, he is here missing. So maybe he will come later. I don't know what will be. So. Um, Okay, I'm starting, and I don't know when they will come and whatever. I have just I have written like little bit. So can I start this? Okay. So in that today's class we will talk about some question answer about quark model as well as quantum chromodynamics. Okay. So in that quark model, basically I was just written something that four interaction, we all know that four interactions are there in present in our nature, and among these four interactions the first one we will not talk about because in in nuclear and particle physics reason the gravity is very much small, so that's why we will not talk about this one. So we will basically talk about electromagnetic weak and strong. So if like all the most of the questions coming from the nuclear and particle physics is totally based on let's say one interaction is there and we have to tell that what type of interaction it is. Is it a electromagnetic, is it a weak interaction, or is it a strong interaction? That type of question is 90%, and the rest of the 10% is different from that. So I thought that I should talk about something more on the type of, like the nature of the nuclear interaction. So here I have given a table. Can you see the screen? Can you see the screen? Hello.
No,
Can you see the screen?
no, ma'am, no.
Oh, sorry. Okay. Then you have to tell me. Sorry. Just a minute. I think I have totally forgot to screen share. Just a minute. Okay. Yeah. Now can you see the screen?
Yes.
Okay. You have to tell. I totally forgot to share the screen. Okay. Just a minute. So here, like a table is there. Can you see the table, right? Yeah.
Yes.
Okay. So in the table, what it is given here, in the leftmost side, I have written some quantum charges, and then conjure, may or may not conjure, and not conjure. So what does this means basically? So in that left figure, like all the quantum charges I have written, like or not all the quantum charges, I was just putting the main quantum charges here. So at the very first, strangeness, then I means isospin, I3 means third component of isospin, P is parity, C is charge conjugation, T is time reversal, CP means charge conjugation as well as time parity, and CPT is the the combination of these three time quantum charges, charge conjugation, parity and time reversal. So now we will talk about that which one is concept in this quantum charges. So basically for strong interactions all the quantum charges are conserved. You can see that for all the quantum charges in that conserved column all the strong is there, like strong interaction. In that strong interaction all the quantum charges should be conserved. But in the when we are talking about electromagnetic or weak interaction, electromagnetic strangeness may or may not conjure, and I means isospin should not be conjured here, but all the things like I3, P, C, T, CP, CPT, all the things should be conjured in electromagnetic interaction. Now coming to the weak interaction, you can see that in that when we are talking about weak interaction, all the things are not conserved in our weak interaction. But here I have done a typo. Here obviously that weak interaction will be here. Like for CPT, all the three should be conserved. I have a typo here. So whatever it is, so that means weak, strong as well as electromagnetic all will be conserved under CPT quantum charge. But there is some quantum charges which may or may not be conserved by EM, or which will be not conserved by weak, and all these things. So when we will talk about one question related to nuclear and particle physics, and when we will talk about the nature of any reaction, we have to remind all the things that strangeness will be conserved where, strangeness will be not conserved where, and isospin, third component of isospin, all these things we have to take in our mind, because this type of things will be very important when we will deal with some questions on nuclear and particle physics, nuclear interactions basically. And also I have made a note here that barium number, lepton number, electric charge, these all three should be conserved in all nuclear reactions. It is like a universal truth that obviously barium number, lepton number and electric charge should be conserved in all the nuclear reactions. Okay, now coming to this type of things I was just mentioning before going to any questions on nuclear and particle physics, because it's a very important, I thought. And one more important thing is that the table, this table is basically talking about some particles, and with that particle the JP configuration as well as parity configuration, isospin configuration, and the total angular momentum configuration as well as charge and strangeness. So this type of table is very important for each and every nuclear reaction. So I was just mentioning here some of the particle contents, but obviously you can, if you want to see all the particle contents, all the strangeness number for all these particle contents, you can see any nuclear and particle physics book. There it is listed like a table form. So here I was just mentioning some of the particles, and obviously their corresponding IJP as well as charge as well as strangeness quantum number. So these type of things will be very much important when we will talk about some questions related to quark model or nuclear and particle physics questions and all this. And also here I was just mentioning some of the more things, like here in the previous slide I was just talking about some baryons as well as mesons. You can see that here all the baryons, as these things are all baryons and these things are all mesons. These mesons, and still there are also baryons. So this type of thing was there. So and in the second slide I was mentioning about all the leptons. 6 lepton is there, electron mu tau and mu nu tau. So all the leptons as well as their corresponding IJP and charge and strangeness. So you can see here in the table all the leptons does not have strangeness number, because all the leptons is not strange particle, like they does not have any strangeness quantum number. So that's why all the leptons have 0s. This type of things is basically equivalent to 0 value of strangeness number. Now in the next next slide, what I was just mentioning, I was mentioning some of the particle with their quark contents. So obviously for all the particles there will be some different quark contents, and we can't remember all the things, but the main particles which will be coming in most of the questions, we have to remember their quark contents, constituents. So here obviously I was just mentioning K plus, K0, K minus, pi plus, pi 0, pi minus, eta 0, eta star, P, N, cascade minus, sigma 0 and lambda 0. I was just mentioning some of the particles and also their quark constituents, I3 numbers, strangeness number, baryon number, hypercharge number and charge. So I thought that it will be very important when we will talking about the question and answer session for quark model as well as nuclear and particle physics questions. So now coming to the first question here. It's a very simple, not that much simple, but still it's a very simple question. This question is basically identify the particles by baryon number, strangeness number and quark content. So I was just mentioning the reaction here. There is two reactions. One is this one and another is this one. So there is basically two questions. First question is that K minus plus P goes to pi 0 plus x 0. This interaction has a unknown particle which is known as x0. We have to find what is the baryon number, strangeness number and quark content for the x0. And the second question is that K minus plus P goes to K plus plus Y minus. So what is the nature of Y minus? We have to search, like nature means what is the baryon number, what is the strangeness number and what is the quark content of Y. Fine. So we will talk about at very first expression. The first expression means K minus plus P goes to pi 0 plus x0. So at first we have to know what is x0 and what is the nature of x0. And obviously we have to find that B, S and quark content. Okay. So before going to all these things, I can tell you obviously that in that note Bini, I can show you that page also. Not here. Here it was mentioned that baryon number, lepton number and electric charge should be conserved in all nuclear reactions. So as it is said here, so that means obviously baryon number should be conserved in that expression also, in that equation also. So baryon number for k minus is obviously 0 because k is a meson, it's not a baryon. Okay, and for p it's a 1 because the proton is a baryon itself, and pi 0 is obviously not a baryon, and if baryon number should be conserved, that means the x0 will be a baryon because only that condition satisfied delta b equals to 0, which means that baryon number is conserved in our expression, in our interaction. Okay, now so that means for x0 obviously baryon number will be 1. Now coming to the strangeness number. So strangeness number for proton is 0 because proton is not a strange particle, and pi 0 is also have a strangeness number 0, but k minus has a strangeness number, and we have to see that what is the value, what is the strangeness number for k minus. I have mentioned here, see here, k minus strangeness number is minus 1. So that means if I write here k minus strangeness is minus 1, so obviously x0 will have the strangeness as minus 1. Okay, otherwise delta s should not be 0. So if delta s should be 0, that means x0 has a strangeness number minus 1. Now coming to the quark content. So quark content. So for these things, what we will do, we have to see the quark content of k minus, p, pi 0. Then we can find the quark content of x0. So obviously quark content of p is u, d. And what is k minus and pi 0, we have to see there, because like I did not remember, but you have to remember. So k minus is s u bar, k minus is s u bar, and pi 0 is what? Pi 0 is, let's say, u bar plus this one. So what will be this one? See here, what should I do for knowing the quark content of x0? We can do one thing. In that left side, what was the total quark content? The total quark content is s u bar u d. So like if you are doing u bar u, then it will be like only one value like thing. So that means if I simplify this, then s u d is there, and in that right side what is there? u bar is there, and this blank as well as, so this blank as well as u bar, it should be s u d, otherwise the quark content will not be conserved, right? So for that case, what will be in that bracket? The in that bracket will be s u d, because u bar will give one value, so obviously s u d will be there. So that means the quark content of x0 will be s u d. Now coming to the charge part, like I was just checking that it is correct or not, because in that expression, what was that expression? K minus plus p goes to pi, what was that? Pi 0 plus x0, right? So pi 0 plus x0. So I will be talking about charge here. So here k minus has a charge minus 1, p has a charge plus 1. So if I just calculate, obviously pi 0 has a charge 0. So that means x0 should have a charge 0, which is mentioned here also. So that means whatever we have doing here, it is correct. So the answer of that question will be that the baryon number for x0 is 1. Strangeness number for x0 will be minus 1, and what was that? Q means quark content of x0 will be USD. So the first question has already done. Now this very similar one, the second question. So the second question was what? K minus plus P goes to K plus Y minus. Okay. So K minus plus P goes to K plus Y minus. So this type of expression is there. First of all, I can search the charge here. Charge is -1 plus 1, and then it is plus 1, so obviously it should be -1, and it is also given here, so it's correct. Fine. Then we will go to the baryon number. K minus is not a baryon, but proton is a baryon, and K plus is also not a baryon, but obviously Y will be a baryon. Fine. Then the quark content, no, strangeness number. So strangeness number, K minus has a strangeness number -1, P does not have any strange number, so 0, and K plus has a strangeness number +1, so we need Y strangeness as -2, because 1 minus 2 will be -1. Now coming to the quark content part. So quark content is what? What was that? U bar S. Okay. So U bar S was there for K minus, plus P is UUD. Now coming to the K plus. K plus will be most probably US bar, but still I am just checking. K plus is US bar, yeah. It will be US bar. Plus what will be there? I have to search for that. So what was there? U bar S UUD. So that means as a combination, what I can write? USD. And in that right hand side, US bar is there and something is there which will make us USD. So what will be that one? See here. Here U is there. So S bar is there, so that means one S will be there, another S will be there, and D will be there, so that as a whole USD will be there. So that means for Y the quark content will be SSD. And obviously is it correct or not? Because for SSD the strangeness will be -2, because for this S -1 is there, and for this S -1 is there, so that means as a whole -2 is the strangeness number for that particle Y. And obviously we can see that from this expression also the strangeness number of Y is -2. So the answer of that question is also written here, that B for Y is 1, S for Y, S of Y is -2, and quark content of Y is SSD. So these three are there. Fine. So that means we can answer correctly the first question of our lecture, that identify the particles by their quantum number, strangeness number, and quark content. Is it understandable?
Yes.
Okay, thank you. Then going to the next question. What was in the next question? Okay, next question is a little bit big, so we will talk only one by one. And I thought that if all the, like, at least some of the people was present, then I thought that I can give you as an exercise and you can do by your hand, and I will do rest of the things obviously, but okay, whatever. So in that question, what was the question? That what quantum numbers, if any, are violated in the following reactions, and are the interactions strong, weak, electromagnetic, or none of the above? So that means the question is basically we have to search each and every reaction is possible or not. First of all we have to search this one, and the second one we have to search that what if it is possible, if it is allowed, then what is the nature of that reaction. Okay, so there are basically 6 reactions I have just mentioned here. So among these 6 reactions, which one is allowed, which one is not allowed, at first we have to search, and what is the nature of that reaction we have to search. Fine. So here I will talk about at first the first one. Let's say first one is that one. So it is 0 plus minus. So this is the expression. Okay. So this is the nuclear reaction. So at first what should I do here? Obviously if any nuclear reaction is allowed or not, we have to search so many quantum charges. How many quantum charges we have to search? Basically we will search here B, L, Q. Obviously Q should be conjugate. B, L, Q, then S, I, I3 and let's say P. But P is not that much important here. Only S, I3, these three are very important for knowing the nature of any nuclear interaction, and is it possible or not, this can be said by these three quantum charges. So for each and every nuclear reaction, at first we have to search that B, L and Q are conjugate or not. If any nuclear reaction does not conjugate B, L or Q, then immediately we can say that this nuclear reaction is not allowed. Okay. Now if the first is already done, that means B, L and Q will be allowed by that nuclear reaction, so that we can go to search for S, I and I3 value for that nuclear reaction. By this method we can find that what will be the nature of that nuclear reaction. So if I write here omega minus, like we are talking about the first question, this one, this one. So here what is the B? At first we have to mention omega minus is a baryon, so that means it has a B1. Cascade 0 is also a baryon, but pi 0 is not a baryon, it's a meson. So that means obviously delta B equals to 0, which suggests that baryon number is conjugate in that expression. Now it's fine. Now coming to the lepton number. Among these three, no one is lepton, so that means delta L again 0. Now coming to the Q part. Q part means minus 1 is there, 0 and minus 1. That means delta Q is also 0. So what suggests it suggests that B, L and Q all are conjugate in this reaction. So that means this reaction is allowed. Now I can tell that what type of reaction it is, like what is the nature of this reaction. To do that we have to calculate S, I, I3. Now coming to the S part. So omega minus has a S which is minus 3. At the very first I was talking that you have to remember some of the particles and with their strangeness number, I3 and all these things, because it's a very important thing. Okay. So cascade 0 has what? I also totally forget. Okay, we have to see there that what is the cascade 0 strangeness number. The strangeness number for cascade 0 is minus 2. Okay, so now coming to that expression again. Yeah. So here minus 2 is there, plus pi minus does not have any strangeness number, so that means it's a 0. So what does it mean? It means that delta S is not equals to 0. So that means the interaction which is allowed, but its strangeness number is not conjugate. So at the very first table I was mentioning that electromagnetic and weak does not conjugate strangeness, but strong interaction should conjugate strangeness. So in that expression, in that calculation of strangeness, we can conclude that this expression cannot be a strong nuclear interaction, because in strong nuclear interaction strangeness should be conjugate, but here we can see that strangeness is not conjugate. Okay, so that means it may be EM or weak. Fine. Now coming to the I part, like see, 3 interactions was there at first, but each and every step we can cancel one, and like one interaction is not possible, then coming to the next interaction, is it possible or not, that type of things will be there. So now coming to the I part, so what will be the I for these particles? That omega minus is only one candidate in their membership, so I will be 0 here. And cascade 0 means cascade 0 has cascade 0 and cascade minus, so that means I is half. And pi minus is what? Pi minus means obviously 1, because 1 because there are 3 members, pi plus, pi 0 and pi minus. And if I am talking about isospin only, that means the I will be 1 for pi minus. Now coming to the delta I case. Here we can see that delta I, in that left hand side delta I is 0, like delta I means that one, I am talking about this one. So in that left hand side I equals to 0, and in the right hand side I equals to half and 1. And as I already know that isospin is a additive quantum number, as well as how much what type of addition is there, vector addition is there. So that means the possible values of I will be here half plus 1, that means 3 by 2 to half. So that means half and 3 by 2 in the right hand side, and in the left hand side 0. So as a whole we can see that delta I is not conjugate here. Fine. So in that first graph, like in that first table, what we were showing here, yes, here, see here in that S case, strong should be conjugate, like in that strong S should be conjugate, but in our expression I already see that delta S was not 0, so that means it may be EM or weak. Now coming to the I part, in that I calculation also I was not conjugate, so that means not conjugate is EM and weak, so it's fine that EM or weak may be there. Now here in that I3 calculation, you can see that in I3 calculation, if I3 is conjugate by that interaction, then it conformly will be a EM interaction. But if it is not conjugate, then it will be conformly a weak interaction. Because only these things is there, like the difference in I3 can say what is the nature of that interaction. Now coming to the I3 part here, like right now we will talk about I3 calculation. Just a minute, where it is. So I3 of omega minus, is 0, and here what was that? Sigma minus, cascade 0 and pi minus. Okay, so I3 of cascade 0 is what? I3 of cascade 0 is half, because cascade 0 and cascade minus is there. Okay, and what was the pi 0? Pi 0 has a I3 value 0, right? Oh sorry, pi minus, so pi minus has a I3 value -1. So if I write here I3 value, in left hand side I3 is 0, and in right hand side I3 is half minus 1, that means minus half, because I3 is a simple additive quantum number, it is not a vector additive quantum number. So obviously here delta I3 is not 0, so that means I3 is not conjugate here. So in that first table, according to the first table, if I3 as well as I is not conjugate in any nuclear reaction, it will obviously a weak interaction, because in that I there was EM or weak interaction possibility was there, but when I was talking about I3 should be conjugate in EM, but I3 should not be conjugate in weak interaction, and in this nuclear interaction we have shown that delta I3 is not equal to 0. That means the nuclear interaction is obviously a weak interaction. Can you understand this point that what I was talking about? Like, we have to see step by step each and every step, so that we can say that okay, this is a weak, or this is a electromagnetic, or this is a strong interaction. You got my point, whatever I was talking? Okay, that is a very interesting thing. Like, we can see, if I do step by step, then we can see that what type of nature it is. Okay, so at the very first question will be like, if I mention here, this will be a weak interaction. Now coming to the this part. Okay, what was that? Sigma plus goes to pi plus pi 0. Okay. Sigma plus goes to pi plus pi 0. Now at first what I was telling, that we have to see that this nuclear expression is allowed or not. So for allowed or not, what we should see, B, L and Q. See here, at first I am talking about B. Sigma is obviously a baryon, so that means B will be, like, for sigma B will be 1, and pi plus pi minus, B for pi plus is 0, B for pi 0 is 0, so delta B is not equal to 0 here. So that means at the very first one is already not conjugate in that expression. So we don't need to see anything else in that expression. We can already tell confirmly that this expression is not allowed. Sigma plus goes to pi plus pi 0 is not allowed because it does not conjugate baryon number. And in our particle physics assumption, baryon number, lepton number and charge should be conserved in all nuclear reaction. That means the second one will not be possible. It's a very simple thing. Okay. So if I write here, then it will be cross. Now coming to this part. N going to P plus pi minus. It's a very interesting thing. N going to P plus pi minus. Pi minus was there, right? P plus pi minus. No. So at first we have to see that it is allowed or not. So B, L and Q. Q is obviously 0 and here plus 1 minus 1. L means 0 0 0. These three are not lepton, so that means 0 0 0. So that means delta Q is 0 as well as delta L is also 0. Now coming to the baryon number. For baryon number, N is also a baryon, P is also a baryon, but meson is not a baryon. So obviously delta B equals to 0. So that means BLQ are conjugate here. That means the nuclear interaction is possible here. Like, it is allowed nuclear reaction. Now coming to the nature of that nuclear reaction. What will be the nature of that nuclear reaction? So for knowing the nature of the nuclear reaction, what should we do? At first S. See here, N, P and pi all are not strangeness. Like, they are not strange particles, so that means all the particles S will be 0. That means delta is obviously 0. So what is the meaning? The meaning of this is strangeness is conserved in that nuclear reaction. If strangeness is conserved, then it can be strong or it can be electromagnetic, right? So, but it cannot be a weak interaction, because in weak interaction strangeness is not conserved. So that means two possibilities there. One is strong or EM. Now coming to the I value. So N has a I value half, P has a I value half, and what was that? Pi minus, right? Pi minus. Pi minus has a I value 1. So if I calculate vector sum, That means here in that left hand side, two possibility will be there. One is 3/2 and one is half. So if half is there, so that means half and half, that means delta I equals to 0. So I is also conserved here. So we can't say here that it is strong or electromagnetic, because in strong as well as electromagnetic, no, right, just a minute. So isospin is conserved here in that expression. So if isospin is conserved here, then obviously it is a strong, because in electromagnetic case isospin is not conserved. I can show you that first table again. Yes. So see, here isospin, I was talking about isospin. So isospin is not conserved in EM as well as in weak. So obviously weak was cancelled for the first one. From the first one weak was cancelled. From the second one I can cancel EM also, because here in our expression I was conserved. So it should be a strong interaction. It can't be a electromagnetic or weak interaction. So as I is conserved here, so that means in that expression, yes, here this is a strong interaction. It is understandable? Yeah?
Yes.
Okay. Now coming to the fourth one. So fourth one is a very simple thing. Like, okay, can you please tell me fourth one is allowed or not? Like, at least you can say that it is allowed or not, because we have, for allowed or not question, we have to see at first B, L and Q number. So if I write here B number, baryon number, so what is the value here? It is 0. It is also 0. This is also 0 and this is also 0. So that means baryon number is conserved. But if I calculate L number, L means lepton number. This is this is not a lepton, that means 0. But mu plus is a lepton. So if I am talking about mu plus, then what will be the value? It is -1, because mu minus is a lepton basically, and mu plus is a antilepton. So for L is -1, E minus is +1, nu E bar is again -1. So here delta L is what? Delta L is -1. So as delta L is not 0, so that means this D expression is not valid. It is not allowed, because lepton number is not conserved here, and lepton number should be conserved in any nuclear reaction. Okay, so that means the D reaction is not possible. Is it fine?
Yes.
Okay. Now coming to this fifth one. Okay, for fifth one I am writing these things. K0 goes to K plus E minus nu E bar. Okay. K0, what was that? I can start from here also. K0, K plus E minus, K plus E minus. K0 goes to K plus E minus plus nu E bar. This type of thing is there. So at first what should I should mention here? The B, L and Q. So B is for K 0, 0, 0, 0. L 0, 0. This is +1, this is -1. That means delta L is 0 here. Q 0, 1, -1, 0. So delta Q is 0. Fine. Now we will talk. So that means B, L, Q all are conserved here. That means this nuclear reaction is allowed. Now coming to the second part. Like second part means strangeness number. So K0 has a strangeness number. K0 has a strangeness number which is, let's see, I totally forgot, but you have to mention, you have to remember that K0 has +1 K plus has plus 1, K0 is plus 1, K plus is plus 1, K minus is minus 1. Okay, so K0 plus 1 plus 1. Okay. So K0 is plus 1, K plus is plus 1 plus 0, 0. So delta S is 0. Now coming to the I part. But one thing I can say you here, that here in that expression nu E bar is as a outgoing particle. You can see here that nu E bar is there. So if in any nuclear reaction neutrino is present, nu E means new electron neutrino. If in any nuclear reaction it is allowed, and in that nuclear reaction neutrino is present, any type of neutrino, electron neutrino, mu neutrino, tau neutrino, any type of neutrino is present, then immediately we can say that this expression is obviously a weak interaction, because neutrino only interact with the matter via weak interaction. They can't interact by strongly as well as electromagnetically. So if in any nuclear reaction neutrino is present anywhere means in left hand side as well as in right hand side in the nuclear reaction, we can say that this nuclear reaction should be a weak nuclear reaction. So as I already see here that in that right hand side the neutrino is present, so we can obviously say it is a weak interaction. But for that at first we have to confirm that it is allowed by saying these three are conjugate or not, because in that question answer session, yes, here you can see that in that D question pi 0 goes to mu plus E minus nu E bar. Here also in that right hand side nu E bar was there, but as it was like delta L was not 0, that means it was not allowed. If it was allowed, then I can obviously so say that it is a weak interaction, but as it is not allowed, then obviously there is no there is nothing to say that what is the nature of that nuclear reaction. It is not allowed. Okay, but in that E expression this equation is allowed, and if in that right hand side neutrino is present, so we can obviously immediately say that it is a weak interaction. We don't need to see the S, I3 values here, because neutrino is there and only neutrino can interact via weak interaction. So that's why we are talking. Now coming to the F part. F part was that lambda 0 goes to P plus E minus. Lambda 0 goes to P plus what? P plus E minus, right? P plus E minus. Okay. E minus. So at first we have to see here B, L and Q. Can you tell me what is the value B here? Like for lambda 0 B is 1, for P B is 1 and E 0. So that means delta B is 0. Can you tell me L value here? Like lambda 0 is a lepton or not?
Not lepton.
No lepton. Okay, so that means 0. P? No, right?
Oh no.
Yeah, and electron, it's a lepton.
It is electron.
So that means it's a 1. So if I write here delta L, it is not 0. So that means we don't want to see Q also here, because that expression is not allowed, because here delta L is not 0. So the last equation is not allowed. Fine? Yeah, I think it's fine. Okay, so I think there were 6 expressions only. Yeah, 6 expressions was present. So we already calculated all the things that among that 6 expressions, some of the allowed and some of are not allowed. And whenever they are allowed, we already mentioned that what is the nature of that nuclear reaction, like is it strong, is it weak, or is it electromagnetic. Okay, so I think this question has done, and this question. So we will come about in this third question. I think time is 6. Okay, let's say only third question, up to third question. In that next question, in that next class, I will talk more about quark model, like quark model questions. So it will be very interesting. So in that third question, what is that? The third question says that the quark system UDS can exist in more than one isospin state. What is the value of I3 for the quark content UDS? What are the possible values of total I values for UDS states? Can you identify with any known particles? Basically, there are three subdivision of that question. First of all, the question is basically we will talk about UDS. The first question says that what is the value of I3 for UDS. Fine. This is the first question. The second question is what are the possible values of I values? What are the possible values of I values? This is the second question. And do you know any example for IDS? This is the third question. So it's a very not that much big question, so that's why I am talking about this question here. So what at first the first question says that what is the value of I3 here. Now coming to the U, D and S individually. So you know that U and D can make a doublet and S is a singlet, right? So if I want to calculate the I3, so I3 for U is half, I3 for D is minus half, and I3 for S is 0 because it's a singlet and only one member is there. So if I3 for UDS is there, so that means what will be the value? Half minus half plus 0. So as a whole it is a 0 value. So I3 has a value 0 for UDS. Fine. The first question has already done. Now coming to the second question. Second question says that what are the possible values of total I values for UDS states. So coming to the I value UDS. You know that U and D becoming a doublet and S is a singlet. So if I want to calculate the I value for this, so I value for U is half, I value for D is also half, but I value for S is 0. So as I already told you that I is a additive quantum, but it is a vector additive quantum. So that means I can have a value half plus half, half minus half in steps of 1. So here half plus half means 1 and half minus half means 0. So what are the possible values of I here? The possible values of I will be 0 and 1. Simple. The second question has already done. Now coming to the third question, that can you identify with any known particles? Okay. So for that you just remember one thing, that UDS is basically a chargeless particle, and it obviously should be a baryon because QQQ combination is there. So if anyone will tell that what is the example for this, you can tell that okay, the example for this will be like lambda 0, sigma 0 something, because for lambda 0 I equals to 0 will be there, for sigma 0 I equals to 1 will be there. So the example what I know from that quantum contents is lambda 0 and sigma 0. If you want more about that, like how can I say that lambda 0 and sigma 0 is UDS combination, I can tell you that if I calculate that S value for sigma 0, obviously S value is minus 1 and lambda 0 has also minus 1, and also here in that UDS combination S only one S is there, and as a 1s has a strangeness number -1, so that as a whole UDS combination also has a strangeness number -1. So we can say that S has a -1 for lambda 0 sigma 0, then lambda 0 and sigma 0 can be the example for UDS, and only difference was in I value. So I value for 0 will be lambda 0 and I value for 1 will be sigma 0. Why? Because for lambda 0 only one member is there, and for sigma 0 sigma minus, sigma 0 sigma plus was there, so 3 members were there. So that's why I equals to 1 for sigma 0. Simple. So that's why UDS combination is only applicable and for lambda 0 and sigma 0. And the example, if I want, then I can give you the example like sigma 0 and lambda 0. So that thing was there in that question. Do you understand that question?
Thank you.
Yeah, okay. So it's already time up. So I had so many questions also, but maybe we can discuss in next class. These type of questions were very interesting, so I thought that it should be discussed, because to identify the nature of the particle, to identify the nature of that nuclear interaction is a very important thing for quark model as well as nuclear and particle physics questions. Most of the question you can see in any competitive exam, these type of things were there, like any x plus x was there, then y plus capital Y was there, and they were just asking that what is the nature of that expression, what was the nature of this nuclear interaction. So that's why I was totally focused on that questions. And in that next class also we will talk about something more on that, that's missing particle, what was that. Then one question, relativistic question was there, so we will also talk about that one. Then simple questions, a simple MCQ type question was there. So MCQ type question I was talking, like I will talk, and one theory based question was there, and one very interesting question I will talk in the next class. It's a very simple theory like thing. So as time has already gone, so maybe we will talk these things in the next
Thank you.
class. Bye bye.